In this video, we're going to learn about two special examples of paths and circuits that have special names. They're named after the people that studied them, a guy named Euler and a guy named Hamilton. The first one is the idea of an Euler path. So this is a path from one vertex to another that crosses every edge of the graph exactly one time. So if you think back to the bridges of Königsberg, this is the idea that we travel across all the bridges exactly once, and it's a path if we start at one vertex and end at a different one, and it's going to be a circuit if it gets back to the starting point. So this is going to be a circuit that crosses each edge exactly once and ends back at the starting vertex. And so this is named after Euler because this is the exact idea of trying to solve the bridges of Königsberg that Euler was trying to do. And he in fact proved this nice theorem here that said that if you have a graph with no vertices at all that have an odd degree, then the graph is guaranteed to have an Euler circuit. On the other hand, if a graph has exactly two vertices of odd degree, it contains an Euler path, but not an Euler circuit. And if the graph has more than two vertices of odd degree, then it contains neither. So if you were to look at the bridges of Königsberg example that we've seen over and over again here, and I'm going to write down the degrees at each vertex here. And you see I have four different vertices that all have an odd degree. That means that we have more than two that have an odd degree. And therefore, by this theorem, that means that there is no Euler path and no Euler circuit. And so basically, Euler created the whole branch of mathematics known as graph theory in order to solve that problem, and he did solve that problem. He had this nice theorem that tells the exact answer. And the fun thing is that if you want to, you can go ahead and, let's say, order some construction here, and let's create an additional bridge along these two islands, and that would change all of the two degrees right there. And as a result, now the graph has exactly two degrees that are odd, which means there is going to be an Euler path, but not an Euler circuit. And we can try to draw it out here. So let's see. It turns out that when you have exactly two odd, you have to start at one of the odds in order to get the Euler circuit, or the path, and end at the other one. So let's start here and go down and then come back and then go across and come back down and go up and back down. And you see I was able to cross every bridge or every edge exactly one time without crossing any of them double. And it's an Euler path, not a circuit, because we started at node A and we ended at node B. So it's a nice little useful theorem here. This fully answers the question about when we can do this, when we can't do this, and it's a pretty easy condition to check by just looking at the degrees. All you have to do is count, and you get the answer. Now the second concept is that of a Hamiltonian path and circuit, and it's similar in concept. Instead of trying to cross every edge exactly once, you want to get to every vertex exactly once. So for a Hamilton path, this is a path that reaches each vertex exactly one time. Whereas a Hamiltonian circuit is a circuit that reaches each vertex exactly once, except it does end at the same vertex it started. And so, again, if I were to draw, I'm getting probably tired of the bridges of Königsberg, but regardless, it's a nice simple graph that we can look at it that's not trivial. And I can go A to B to C to D back to A. That would be a Hamiltonian circuit because I reached all vertices A, B, C, and D once, except for the fact that I ended up at A and I started at A. So technically A was there twice, but that's needed for a circuit anyways. And if you just did A, B, C, and D, that would be a Hamiltonian path instead of a Hamiltonian circuit. Now, Hamiltonian circuits are in some sense easier to get in that you don't have to have exactly these odd degrees or no odd degrees in order to get one. Right? The bridges of Königsberg, there was no Euler circuit or path, but there is both Hamiltonian circuits and Hamiltonian paths here. So like I said, you can kind of think of it as being easier, but it's going to turn out that just finding any old Hamiltonian circuit is not what we're going to be interested in. Instead, we're going to be looking at something called the traveling salesman problem. So let me explain what that is. What we're going to do is we're going to take a little variation on what we've been doing. And when we draw our graphs and we draw our edges, we are going to not just draw the edges, but we are going to put numbers on them. So let's say 3, 5, 1, 7, 8, 2. And the idea is these numbers here, they're called weights, and they somehow indicate a length or a difficulty or some other way of measuring difficultiness of traveling along that path. So for example, if you have two different paths from A to B, maybe one of them is taking surface streets and one of them is driving on the freeway. And as a result, they're going to have different amounts of time associated with them. So you could think of the weights in that case as being how long the trip takes. Other cases, let's say you're flying, maybe these numbers represent the cost of the ticket. So flying from one city to the other on one airline would be one price. If you have a different airline, it'd be a different price. Or if you fly different cities and so on. But the idea is that you have these weighted graphs where all the edges have a number associated with them. And then you're no longer trying to just find a Hamiltonian circuit. You want to find a Hamiltonian circuit that has the smallest total weight. So I can write this out here. This is the problem of finding the Hamiltonian circuit of smallest total weight. And what do I mean by that? What's this total weight? Is if you were to say, take this path here, you'd have 3 plus 1 is 4, plus 8 is 12, plus 2 is 14. My total weight would be 14. And the question is there a different way I could travel around that would have a smaller total weight? Now, the reason why this is called the traveling salesman problem is that back in the day when we had more people that actually were salesmen that would travel from town to town to sell things, they would need to either drive between several cities, or if not drive, fly between several cities. and they want to try to find the most efficient way to get around there, where they reach every city exactly once, so that they can try to sell their wares there. And at the end of the day, they get back to their home city, which is their starting point. So they want to travel anywhere, say Los Angeles, New York City, St. Louis, whatever cities they want to travel to. They want to reach each one of them exactly once, and then get back home at the end of the week or however long the trip is. And they don't want to go to a city more than once because they already sold there. They don't want to try to waste their time selling to people they already bought. So that's why they want a Hamiltonian circuit here. So this is a pretty famous problem. Unfortunately, I cannot just give you a quick theorem that answers the question. There is no such one right now. In fact, for those of you that study unsolved problems, you can learn something called P versus NP, and how difficult problems are. And the traveling salesman is a very classic example in that field. But to suffice it to say that this is a very challenging problem overall. I do not have a perfect answer for you on how to solve traveling salesman. As far as I know, there is no perfect answer. On the other hand, I'm going to show you a couple algorithms that'll at least get you something. It may not be the best solution, but it can at least give you a hopefully reasonable solution to the problem. That'll be in a later video.